So for SP5a, which is ray diagrams, the first thing that we're going to look at and that we need to be able to do, and a lot of this is actually from SP4 anyway, but just to make sure that every single part of a ray diagram that we need to be able to draw if we're requested in the exam is basically shown in this diagram here in a simple reflection diagram. So if we have a look what we've got the barrier or the mirror in this case. It's a reflection, so we'll assume that this is a mirror of the surface. And what we've got is this line coming in, bouncing off the mirror at this point and then coming out. Now what we need to be able to do is make sure that during the exam, when we're drawing our ray diagram, that we add each of these elements into the diagram so that we know that we've got all the different pieces that need to be put together to get a correct diagram. So the first thing we're going to add, at the boundary, wherever the light ray either enters or leaves or is about to cross the boundary, we need to add our normal line. So a normal line should be drawn as a dashed line, and the reason is just because we want to differentiate between the normal line and the light or the waves themselves. So the normal line is usually this dashed line here, but the normal line is always, and the name is such because of this, but the normal line is always 90 degrees or perpendicular to the boundary at that point. All right, so it may not be a vertical line, it is here because our boundary is horizontal, and therefore 90 degrees to that is a vertical line here. And in this specific example, if this were a mirror, we know that the light is not going to pass through the boundary, we know it's going to be reflected off. So our normal line only needs to be above the boundary. So 90 degrees to the mirror is here, the dashed line, so we know that it's not a wave, we know it's a normal line. And it only goes above the boundary and not below because we know the light ray is not going to pass through. All right, I'll show you another example where it should go above and below. Then we're going to add an incident ray, so the third one on the list. That will be this red line here. So the red line coming in really should have an arrow on so we know exactly which direction it's coming in. So we're going to say it's coming in this way. And that's the incident ray. Now a ray on your ray diagram is simply just a straight line which represents the direction that the wave is traveling or the direction that the energy of the wave is traveling. So we know from chapter 4 that waves can transfer energy and information, and also the direction of the wave is in that same direction. So an incident ray, the ray itself just represents the direction of the wave and the direction of the energy. It's not a real wave, it's just a line that we draw so that it makes these diagrams much easier to see, and it shows us what happens to the waves at different points. So the ray is not actually the wave itself, it's just the direction that the wave would go. The reason it's called an incident ray is because this one is the one that's actually entering the boundary. It's incident, it's going into the boundary. So the incident ray is the one that goes into the boundary. So as it enters. So that's the incident ray. Now obviously therefore, the one that is reflected off is known as the reflected ray. Okay, so again the straight line is the reflected ray. It was reflected off the boundary, so it's the reflected ray, and technically that should have an arrow on there showing you that it's traveling in that direction. Now we've got the two rays coming in and reflecting off. We've got the normal line at 90 degrees to the boundary. What we can add now are the incident angle and the one that's already on here, which is the reflected angle. Now what we need to make sure we're doing, which a lot of students forget to do, or they always make this mistake in the exam, is you must draw and measure your angles of incidence. So the incident angle would be the angle at which the light or the wave came into the boundary, and then the reflected angle, which is the angle at which it leaves the boundary, must always be measured from the normal to the ray. So in this case you go from the normal line to the ray, and we draw the incident I from normal to ray on the ray coming in. So always from the normal to the ray, never this angle here from the boundary to the ray. It's never from the boundary, always from the normal. And therefore obviously you have on the other side the reflected angle, which is the angle between the normal and the reflected ray. Now just to make a note of the law of reflection in general, so if we're drawing reflection diagrams, we should know that a reflection of a wave from a boundary happens at the same angle as it enters. So the incident angle is equal to the reflected angle during a reflection. All right, so I is equal to R for reflection. The only other thing really that we can draw on a ray diagram, everything we have so far is fine in terms of telling us what will happen to the wave if it passes through the boundary. For example, in a second we'll look at a refraction, or if it bounces off and reflects, what will happen. But it doesn't help necessarily explain why it happens or how the refraction takes place. So one more thing we're going to add, as you can see, are these blue lines which are perpendicular to the ray, but they're parallel to one another. So these blue lines which are parallel to one another are known as wave fronts. Now the wave fronts are the real wave. If you were to see the wave passing through the water, for example, a transverse wave passing through the surface of the water, and you were to look at those from above, then you'd very likely see the peaks of the wave as quite bright lines, and then you'd see the troughs, those dips in the waves, as shadows. And you could see those quite clearly as parallel lines next to one another traveling in that direction. So our wave fronts are essentially the peaks of the waves. So they are specifically us looking at the waves coming in. All right, the ray itself is just a line for a diagram to help us basically simply draw a diagram and to know the direction that the wave would be traveling and the direction of the energy. But the wave fronts, which is probably the one that we use the least in diagrams, but the wave fronts are the true waves. So we can see the peaks on those waves. And we saw that in chapter 4 as well, which helped us explain why does refraction happen and why does it turn this way and why does it turn that way, if you check the SP5a on refraction. So those wave fronts can also be required in a diagram as well. And actually, just to add, the gap between each wavefront is lambda, which is the wavelength of those waves. All right. If we want to look, so for example, we're going to draw a ray diagram, but we're going to conduct an investigation where we're looking at how light might refract through a glass block. So if I draw a rectangular glass block, so this is one of the core practicals that's required for the GCSE in chapter 5, it's the first one. What I'm going to do is I'm going to pick a point on my glass block where the light is going to enter. Now I've chosen towards the left specifically because when the light refracts through, I know that it's going to leave on the other side a little bit further over, and if I keep choosing bigger incident angles, then the light rays are going to come out further and further, and I might miss the edge of the block. So if I start a little bit to the left, then I'm covering myself further on to the right. The first thing we're going to draw is our normal line. So we always draw a normal line as a dashed line. And again, our boundary is horizontal, so the normal line will be perpendicular to that, which is 90 degrees to the boundary. So it's a vertical line again for this one. It's at the point where the light is going to enter the block. Obviously, a normal line would be useless if the light came in here and I drew my normal line over there. It doesn't help me because it's not at the point where the light enters the boundary. And obviously, what I was saying before, in this specific example, my normal line should go above and below the boundary, not just above. Because the light is going to enter the block, I need to know what happens relative to the normal line inside the block as well. All right? So what we're going to do is we're going to change the incident angle. We're going to look at what happens to light when it passes through this glass block. It's air on the outside, glass on the inside. I want to know what happens when light travels through, but also what happens to it as it's traveling through at different incident angles. So if you remember, we always measure an incident angle from the normal to the ray. So if I go from the normal to the ray, that's my incident angle, and I might try 10 degrees as my first incident angle, first light ray that enters the block, 10 degrees. Use my protractor, measure 10 degrees from there, and there's my first one. Then what I'm going to do is I'm going to try a range. So I might try a bigger incident there, an even bigger one there, and all the way, stretch it as far as I can, going all the way over here. Obviously that's not 10 degrees, but on your protractor you could go 10, 20, 30, 40, 50, 60. I'll draw a quick table up here. I'll call that incident 1. What's going to happen is we're going to get light passing through with a refracted angle R1, incident 2 and refracted 2. And these will make more sense in a second when I show you what the diagram's going to look like. So you've got your different incident angles coming in. We drew them already, so all I need to do now is place the glass block back on the outline that I drew before, switch on my ray box. You'll know what the equipment is at this point. You've used the equipment, you've got a ray box with light, shine the light through a focused beam, and you can line it up with these incident angles and see what happens when it goes through the block. What's going to happen is you'll see the light. You won't see it on the inside of the block. You can't see it from the outside looking in. But what you will see is on the paper as it leaves is you'll see the line which leaves the block at the bottom. So you'll draw 2 points on there just so you can draw a straight line joining it back up to the boundary. For the 10-degree one first, it leaves the block there. How do I know where it was on the inside? I'll remove the block from the page and I'll just join those 2 lines from that point to that point, and that must be the journey or the path that it took on the inside of the block. Now, before I start measuring any angles to fill in my table, what I'm going to do is I'm going to draw a new normal line, again at the second boundary where the light ray leaves, where the light leaves the block, and that's again 90 degrees. Because this is a horizontal boundary, the normal line will be 90 degrees. So I draw my 90-degree normal dashed line above and below because it's passed through, and now I can discuss, or I can measure the angles relative to my normal line and see what happened to the light as it came in and left. So the first angle I'm going to measure here is R1. So this one here is the refracted angle when it went through the first boundary. So incident angle entering the boundary, refracted angle when it went through. Now as you can see, this should be slightly smaller than this one. The light has actually refracted towards the normal, which we expect because we know that in chapter 4. The light slows down, it refracts towards the normal. So this one is smaller. So I've got my incident one is 10, and I'm going to make this up, but this one is smaller. So let's say this one might be 5 degrees. Now I know because of geometry that this one should be the same as this one because of the alternate angles or Z angles, so it should be the same. But I'm going to call this one incident 2 because this is the incident angle for this boundary, so it's entering the second boundary, it's an incident. And if I measure it with a protractor, I should get what I did get before, which is also 5 degrees, so it's the same angle. I'll measure it for accuracy and just check that. And then what I'm going to do is, as you can see, this is the refracted angle number 2. This light ray we know should be parallel to this one simply because these 2 boundaries are parallel to one another. So because they're parallel to one another, the ray that enters and the ray that leaves should also be parallel to one another. So the angle here should be the same as here, but again, things can happen in an investigation, accuracy might not be 100%. So I'm going to measure it with my protractor, I'm going to check, and I'll say in this example, yes, it's 10 degrees again. Alright, and then all I'm going to do is I'm going to increase the angle to 20, shine the light, see where it leaves. It could be somewhere like that. Draw a normal line on, join the lines up again, and then measure I1, R1, I2, R2, and it should be those 2 are the same and the 2 in the middle are the same. Now, quick conclusions that we can make if we draw a graph. We've got incident angle on the x-axis, refracted angle on the y. For air to glass, so this one, incident was always bigger than refracted because it went towards the normal. So I is bigger than R. You can see that in the data, or we could, if we kept going 20, that might be 13, 13, and 20. So I is bigger than R. You can also see that as you go along, it increases, should look something like that. So as I increases, the incident angle keeps getting bigger, the refracted angle also gets bigger. It's still less, but it is getting bigger as well, so it increases. But if you follow the graph, you can see that towards the higher values, the graph is not a straight line all the time. It starts to curve, so it means it's not actually directly proportional. It is incident goes up, refracted goes up, but it's not directly proportional. And that's essentially the core practical for refraction. If we carry on, the last part of 5a that we need to learn and we need to look at is something known as total internal reflection. Now, this is a very, very simple diagram of what's going on. It's very clear that the light that enters here, the red laser light, enters the glass here, it bounces off there, and then it continuously reflects on the inside of the glass block. Now, this is the best image to demonstrate total internal reflection. The light is reflecting internally in the material. But because you can see the light is clearly coming out of the glass, you can see it, so it must be leaving the glass into your eye. It's not perfect TIR. It's just an example. You can't see it. If it was perfect TIR or perfect total internal reflection, then you wouldn't see any of the light. You would just see what we did before on the glass block. It would all go through and you wouldn't see it until it came out the other end. But this is the only way to actually show what is happening inside the glass for that light to be reflecting. So it's internal reflection, not necessarily total, but it is internal reflection. Now, what's the theory behind total internal reflection taking place? 3 simple rules, okay? Every material which is higher refractive index than the material on the outside, so this will only happen from glass to air or water to air, from high refractive index to low for light, so when it's going to speed up through a boundary. And the three things that you need to know: the critical angle for every material is different, and it is specific to what happens when the light meets the boundary at that critical angle. So what does that mean? If we had light on the inside of glass, for example, with the outside being air, so high to low refractive index, and we start with different incident angles when it reaches the boundary, so the incident angle here is 0, 20, 30, 40, increasing up to 60. All these incident angles here, just normal refraction through a boundary. High to low, the light speeds up, it refracts away from the normal. It's just simple refraction, okay? All these are simple refraction. Then when you get to a very specific incident angle, which happens here, which is 48.8 degrees for this glass, so very, very specific angle. When we get to an incident angle that is 48.8, something slightly different happens. It's still refracted, but it's refracted at a perfect 90 degrees. So what you could say is, when the incident angle of light is equal to the critical angle of the glass or the material, then the light will refract along the boundary. Okay, so at the critical angle, the light will refract along the boundary, which is a refraction of 90 degrees. So incident angle less than the critical angle, then it's normal refraction through the boundary, which will be away because it's speeding up. Incident angle equal to the critical, refraction along the boundary, or refraction of 90 degrees. What happens if you go above that incident angle, where it's above the critical angle of the material? Well, it can't refract greater than 90 degrees, because if it refracts anymore, then what's happening here is actually a reflection now. So if it goes past the critical angle, if you're greater than the critical angle for your incident angle, so 60, which is greater than 48.8, then total internal reflection will take place. The light will reflect back inside the material, internally reflect at the same angle, because the law of reflection says incident angle equals the reflected angle. So this example here is TIR, or total internal reflection, 60-60, because the incident is greater than the critical. If the incident was equal to critical, it would go along the boundary, refract along the boundary, 90 degrees. Incident less than the critical, it would be normal refraction through the boundary. That's it for 5a, but what I want to do is give you a specific example of how you do this experimentally. So if we had a semicircular glass block and we wanted to show or demonstrate total internal reflection and actually find out what is the critical angle of this material, this glass, then we generally use a semicircle so that we can get the light going through at the same point, and then the incident can change at the same point. So what I'm going to do on the semicircle is, I need to shine the light on the inside from this curved surface. I need to shine the light through the curved surface to the inside of the glass, so that it hits the center of this flat surface here. Now, the only way to get the light to go through the curved surface without actually changing its direction when it enters is to shine the light along the radius. And the reason for that is, if I do this from the center along the radius there, the light goes in. I know this is the radius because it's from the center. So if I measure the flat surface and I halve it, I've got the center point. Any point from the center to the edge of the circle is a radius. And the reason that the light passes straight through along the radius without changing direction when it enters is because it's coming in along the normal line. The incident angle is 0. It's not coming in at an angle or 90 degrees to the boundary. We know that all the wavefronts enter at the same time, no refraction. It still slows down, but there's no refraction, so it goes straight through. So in this investigation, if I want the light to go through the block to the center without refracting, I must shine the light along the radius. All right? What I'm going to do next is I'm going to add my normal line again. So I'm concerned specifically about what is going to happen to the light when it reaches this flat boundary from inside the glass. Inside the glass, because total internal reflection only happens from high refractive index to low refractive index. Okay? So my incident angle is from the normal to the ray, and it's here. Now if I did this for an incident angle of around 20 degrees, then what would happen is normal refraction, as we said, away from the normal because it speeds up and it just refracts through. That tells me that this incident angle is less than the critical angle for this material. What I'm going to do is I'm going to keep increasing this angle until I get to an incident angle where the light ray goes perfectly across the boundary. So what's happened, not a great drawing, but what's happened here is the light has refracted along the boundary. I know that this angle is specifically the critical angle of this material. Whatever that happens at is the critical angle. So let's say this incident from normal to this ray, where the light refracted along the boundary at 90 degrees, that angle there was 50 degrees. The critical angle of this material is 50. Now, let's test it. If I just go above that 50 degrees to 51, so I go a little bit higher, then I know that I should get total internal reflection. So anything greater than that critical angle, you should get total internal reflection. And that's how we do it through a semicircular glass block in an investigation in the lab. All right, and that's 5A.